Good afternoon, everyone. Hope you are hearing me. Today we are going to discuss the transient analysis and the application of the Laplace transform, and we'll cover a little bit about the Laplace transform and its application for transient analysis. Then we'll discuss about the transform of the circuit elements. Then if time permits, we will definitely cover up the second order system, how to solve it in the time domain. That means second order transient systems, that which involves inductors, capacitors, right? Both inductors and capacitors, you will have one second order transient circuit. So how to analyze it from the time domain point of view, and also by applying the Laplace transform. Okay, let's start. So I will be minimizing the video. I'll be removing the video now. So that you can have a better view of our class. First of all, why Laplace transform? Okay, I'll go through one by one. So Laplace transform method is a very powerful tool for analyzing the transient circuit, right? It's a powerful tool. It transform an integral different. We have an integral differential equations. Whenever you have capacitors, inductor, and resistors. Let's say you apply you have a switch here, C L and R, and you have a voltage here. So transient inverse. So you will have when you write the KVL. So it is simply Ri plus L di upon dt plus 1 upon C integration of I dt equal to V. This is called the integral differential equations. It involves integration, it involves the differentiation, it involves the variables. So it is called the integral differential equations. Then what you will do in the time domain, you need to differentiate again, so that you have one second order differential equations. But in the Laplace transform domain, right? In the Laplace transform domain, what happens? We apply the transform for each element, or you can also say that we can simply in a single go we transform the integral differential equation into a algebraic equation. So you know that it is very easy to manipulate the algebraic equations. So in that case, what we'll do, we'll factorize that algebraic equations, and before that we know the Laplace transform pair. For example, ut, that is a unit step function, has the Laplace transform of, if you have ut, it has a Laplace transform of 1 upon s. And for example, you have a del t, you have a Laplace transform of 1 e raised to the power minus 5t ut has the Laplace transform of 1 upon s plus 5. So when we factorize the transform equations and we look up for the transform pair table, then in a one go we can find the time domain domain solution for the circuit. So that is the inherent advantage of application of the Laplace transform. It gives the as I told you, it gives the complete solution in one operations. Then initial conditions are automatically specified in the transformed equations. Whenever you have all the variables, you have initial voltage across the capacitors, initial current through the inductor, so it will be taken care of during the initial transform. When we are doing the transform, it will be taken care of. And LT pairs are readily looked up, as I told you. Laplace transform pair we know, and we can easily look up to find the corresponding function in time domain. So before going to application of the Laplace transform, we'll discuss little bit about the Laplace transform. And because we are going to apply the Laplace transform in the transient circuit, definitely we should know what exactly Laplace transform, how it is found, but more detail about the transform it will be covered, or you will be covered in the signal and system. There are a lot of transform. There is G transform, Fourier transform, Laplace transform, discrete Fourier transform you will be studying in the, but for the application specific view we will discuss the Laplace transform here also. So you know that whenever before that I want to say something very fundamental. Okay, here, okay, we'll only consider unilateral Laplace transform. Okay, and it is unilateral Laplace transform. First case, and inherently all circuits, I mean these are the LTI, linear time invariant. Inherently circuit we are analyzing are LTI, that is linear. I have told you it's composed of a linear element, inductor, capacitor, resistors, and also time invariant. Time invariant in simple term that will be covered in the your signal system. Time invariant in very basic terms I want to emphasize that, for example, suppose you have a system or network. Let's say we are discussing network here, network. You have given a Vt and you need to find the V0 t, Vit V0 t. If the switching takes place at t equal to 0, let's say the what, let the same Vt, let's say Vit is like this. Suppose you have applied the u of t as an input. Let's say your output is, let's say, like this, starts from 0 and goes up. If this network is linear time invariant, okay, then if I shift the input, let's say initially at t equal to 0, let's say I shift this input at t equal to 3, that is 0, 1 as usual. That means I applied the u t minus 3. So obviously my response will be only shifted without any changing the system property. The response will be exactly same without changing the, let's say it is 2. You see both the response are same, only the output is shifted by 3 unit or 3 second. That is called time invariance. Another example I'll give the time invariance, that suppose you have let's say with respect to you have an equipment in your home. For example, you have an LED TV. If you on your LED TV today, it will be functioning and displaying all the channels, provided you have subscribed the channel, that is the DTH channel. Okay, suppose I am assuming that you have subscribed all the channel for the TV. Then you switch off the TV, then you come after, let's say you don't have any time for next 5 days. Okay, on the 6th day you again on your TV and you browse the channel, you hop the channel by one, again you are checking that all the channels are working fine. That means your TV is called the time invariance. That means its property does not change with time. It is not, if it is not malfunction, that means TV also acting as a your time invariance. That means you are not changing with the time. It also can be a time invariance also can be applied in a abstract situation. For example, if somebody is pickling his mind, we might say that you are very variable, or you are varying with the time. Okay, if your property or your behavior is not does not change with the time, then we call the time invariant people. Okay, so Laplace unilateral Laplace transform will be applying the LTI system. That is the network is itself inherently we assume as a LTI system. So let us discuss the Laplace transform. Inherently we will discuss here only unilateral transform. Let the signal or the variable be x of t. Then Laplace transform of xt is denoted as capital X of small s and defined as a 0 minus, see the lower limit, 0 minus to infinite x of t e raised to the power minus et. Okay, e raised to the power minus st dt, and okay, and this lower limit is 0 minus is to capture the discontinuities at t equal to 0. For example, del t is the discontinuity at t equal to 0. Okay, or u of t, it is discontinuity at t equal to 0. So to capture this discontinuity, we use 0 minus, but for time being you need not to worry about this 0 minus. For signal to have Laplace transformable, okay, a signal, because everything in a circuit, in a signal point of view we are generalizing. In the circuit point of view, you have a limited energy source. For example, a constant current source, it has a limited current power. For a constant voltage source, it has a limited voltage and also power. So for this to be Laplace transformable, then we can say that when you integrate absolute value of t and the real part of this s, t dt should be less than infinity. What is this delta? Actually, this s is called the complex frequency sigma plus j omega. This is the real part of s. Sigma is called the real part of s. Okay, so we'll see that in later on that the region in which, okay, region for which this Laplace transform is valid. Let us go by the example. Suppose you have x of t, is equal to a e raised to the power minus small a t, okay, smaller t for t greater or equal to 0. And also we are assuming that a also greater than 0, that means a is positive. A is positive. So by definition, x of s is equal to 0 minus to infinity a e raised to the power minus t e to the power minus st et, which is equal to a 0 minus to infinity e raised to the power minus cos s t et, which gives you the a to the power minus a s plus a integration of e to the power at is the 1 upon a e raised to the t. So minus a plus s t 0 minus, okay. So it simply becomes minus a plus a e raised to the power minus a plus a into infinity minus, when 0 minus 0 plus, it does not make any change in this case, e to the power minus 0. Now a minus s plus a. Look at this. So I can write like this: e to the power minus a plus sigma plus j omega into infinity minus 1. But you see here, this e to the power minus j omega infinity, this magnitude is always 1. Its magnitude is always 1. But to make it this term 0, this term 0, so we split this e to the power minus j omega into sigma into e to the power minus a plus sigma into infinity. Now you see here, if I make, because you know e raised to the power minus infinity equal to 0. So if I make this a plus sigma is greater than 0, that is positive. So overall this will be e to the power minus infinity will be 0, and that this will be 0 into this, so it will be 0. So your x of s becomes a upon s plus a, provided these conditions, that is sigma is greater than minus a. Sigma is greater than minus a. What is this sigma? That means is the real of s is greater than minus a. We have assumed a equal to positive. So this is called the region of convergence. Region of convergence, how it is shown in the s plane. This is your sigma real axis, this is your imaginary axis, this is the all point are existing. So you can easily say that real a is greater than minus a, this is 0. If a minus a is here, this is a line, real s equal to a. Let's say I say y equal to, sorry, x equal to minus a. This is a straight line drawn parallel to y-axis. So this, that means this line, beyond this line, that is the towards the negative axis, does not exist, does not valid. But in this range, beyond right hand side of the x equal to or sigma equal to minus a, all point it is valid, every point it is valid. As we are assuming that all the networks are causal, because we will always have the right hand side ROC. When you go for the signal and system, you will find that ROC may be left sided, ROC may be right sided, ROC may be a strip like this. Some ROC may be like this. Let's say this is your minus a point. Some ROC is the strip of, that is minus a to minus a by 2, this strip. So that will be a part of your signal and systems, and lot of questions also coming from that topics in the competitive exam. Determine the ROC. Okay, we are not bothered about the ROC here because we will be applying the Laplace transform for the transient analysis. Also, here as the system or the network is inherently causal on the electrical network, because causal means until unless we applied any signal, the response is 0 for a initially relaxed system. So it is a causal system. Or we can split the, if you have some initial voltage or current, we can call that this is the system, causal system, but initially not rest. We can divide it in two categories: initial rest causal system or causal system which is initially not rest. So we know that, so your e raised to the power minus at u of t has the Laplace transform of 1 upon s plus a. Similarly, you can find del of t is equal to 1, u of t which is equal to 1 upon s, then cos a t ut, okay, that means starts from t equal to 0, that is s upon s square plus a square. Sin a t ut as the Laplace transform of a upon a square plus a square. Suppose combination of e to the power minus a minus bt, bt, b is positive, okay, sin a t ut. So replace wherever s with the s plus b, okay. So a upon s plus b square plus square, e raised to the power minus bt cos a t ut as the Laplace transform of, wherever s you have to replace s plus b, that is the property we will discuss, s plus b upon s plus b square plus a square. These are the commonly encountered the Laplace transform pair, okay. I assume that you know that all these shifting, all these things, right? Otherwise I will discuss little bit, okay. What is a del t? Can anyone say? This was the question asked me. They asked me in the interview question this year. Del t is equal to infinity. Normally people write 1. They are confused between the del t and del n. Infinity for t equal to 0 and 0, t not equal to 0, and another term you should not forget, integration minus infinity to infinity del of t dt is equal to 1. That is area 1, but the value is, this is that's the impulse, the value is infinity, okay. So then what is the ut? Ut is so how to represent in the uh, graphically is represented like this, a arrow to indicate, but normally it is written 1. 1 indicates area of this impulse is 1, not the absolute value, not the amplitude. Amplitude is the arrow, so it is infinity, okay. So now u of t, the fundamental unit. So u at t equal to 1 for t greater than 0 and 0 t less than 0. We are not bothered about the what is the value of t at 0. So because it is discontinuous, okay. ut equal to this, okay. And how to represent it graphically? So ut will be represented like this. So t equal to 0. So it a step. Why it is called? It is a step jump from 0 to 1 time x. right? Now another term is the R of t, RT, RT is TUT, and how to represent this is simply ramp. So slope, you know, it is the slope is V1. So we represent slope 1 like this one. Okay, we'll cover one by one. There is also manipulations. So some property also del t which will be useful. Okay, so more it will be discussed in the, suppose you have been given x of t is the 3 del t. So it means 3 is the area, not amplitude. Okay. So another thing about the del t is the, for example, x1, these are the important, so you should know x because it is area, so it is always varies when we have a that is a compression or expansion in the time. Del of 2t, it is not same as the del of t. Actually del of 2t is equal to simply half, that is area is remains half actually. Okay, area half. For example, x2t, proof not required. Okay, proof actually not required, but proof if you want, then you have to first define the actually what is the del t. Del t is actually not a function. To we are having a distribution. You know normal distribution. This is actually distribution. But in this normal distribution, you know it is root over 2 pi e raised to the power minus x square upon 2. Okay, x square upon 2. Now you are the, here is the your sigma, let's say sigma, and this is your sigma square. What happens when this sigma is the variance, sigma square is the variance. So if you decrease the variance, when you decrease the when you decrease the variance, what happens? This will be more and more, area remains 1. Okay, you have a area remains 1 because you know the distribution function of the area remains 1, but it goes and spiking. Sorry, I did wrong. Okay, I'll show you. When you decrease this variance, let's say initially you have this distribution, now you decrease the variance, this will be like this, and again this decrease the variance. So it is keep on, and when this variance tends to 0, so this will be represented as a spike, but area remains 1. Okay, so you can okay, t means, okay, x of t means here also t. So with using this definition of the impulse, you can easily, if you try yourself, you can easily derive all these, that is your what you call scaling properties. Why, how del of 2t becomes half del t. Similarly, let's say similarly if del of half of t, it means exactly twice area of del t. So it will be very useful. Okay. and del of t is same as the del of minus t. Okay, again you need to know the folding. Okay, just go through and just remember, I will be also going for the simple manipulation of the function. Now suppose you have given x of t, x of t, x of x3t is equal to del of 1 minus 2t, because it is a, here it is a scaling. As you know, the area will be half. You can easily understood that area will be half, but it is a shifted version. So for this you can write like this: first half, take out the 2 here, so half minus, okay. So you know that it is scaled by 2, so area remains same, del of half minus t. It is same as the half del of t minus half. Okay, so now I will go to the going to discuss about the simple manipulation, shifting. Simple signal manipulation. First one we will discuss the shifting. In shifting, what do we do? Either we advance, either we move left, shift left or shift right. For example, you have a signal like this. Suppose I want to shift left, it would be looking like this. Shift left. If I move the, let's say it's a 0 and this is a 3. So I shift is a minus 1 and 2 obviously. And if I shift right, so this will be 1 and this will be 4, right? Just shift right. Yes or no? So we will formally define shifting. Let the function x of t plus t0, okay, is the signal, same signal is the same signal but delayed by time t0 if t0 is negative. This is called the delay. Shifting right means it's a delay. We delayed it. You just think yourself. It is supposed to start at t equal to 0. It's supposed to start at t equal to 0. But now where it starts? It delayed by 1 minute or 1 second. So this is the x of, because this t0 is negative, so t minus 1. X of t minus 1. Advanced by t0 if t0 greater than 0. This is this one clearly advanced version. It is supposed to start at t equal to 0, but now it is starting at t equal to minus 1, advanced by 1 second. So it is x of t plus 1. Okay, hope it is clear. We will discuss another example. Let us x of t looks like this: 2 and let's say 4. Obviously 0 will be somewhere here. Okay, let us find x of t plus 3, another one is the x of t minus 2. So what you understand by this first one, x of t plus 3, that means it is shifted left or right, because it is a advance is always shifted left, so it will be shifted left by 3 unit. Means how will write it, the same signal but shifted left. When you have a shifted left by 3 units, so just minus 3 here and 4 minus 3 here is simply minus and minus 1 and 1. Okay, clear? Or you can just simply count 3 unit, here 1 unit it will be 1, 2 unit that is 0, 3 unit minus 1, either way. Now x plus t minus 2, it is advanced by, sorry, it is delayed by 2 unit. Actually it should it should start at 2, but it is delayed by another 2 unit. That means actually it will start at the 4. 2 plus 2 and 4 plus 2, which is 6. So very simple. So do the signal. This is actually part of your signal system, but we'll be applying all these things in the network theory, so you should know. I hope you know already, but I want to discuss in my way also, my way of learning. Now come to the folding or reflection. Actually, actually a lot of things we need to know about the Laplace transform, then Laplace transform pair, then we call the waveform synthesis also there. Today we may not be able to discuss the application part. Then besides expansion, okay, lot of things are there actually. Okay, we learn first, otherwise just going by the theory or questions won't help you without learning. So folding, folding or reflection. Lot of people confuse about this property. Okay, but one simple thing will, if you remember, you will never forget how to do the folding. Folding, let the signal be x of t. The folding operation, the signal becomes x of minus t. So it is actually mirror image of x of minus t is mirror image of x of t about origin. Remember this term, about the origin. You need to find the x of minus t taking the image mirror about the origin along the time axis. So example, let's say you have u2 know x of t is equal to u of t. That is, this is, find the x of minus t. So mirror image about the origin. Put a mirror here and see the image how it looks. You put a mirror here, like you put a mirror here and you stand here and look here. How the mirrors look. Obviously this will be looking like this. Yes or no? So this is the x of minus t. Another example. Let x of t is equal to this. Graphically I want to show. 0, 1, 2, 3. Let's say 2. Okay. What will be the x of minus t? Put a mirror here and see how the image looks. How it looks? Obviously it will start from here. The mirror, the distance will be here and it will go like this. Minus 1, minus 2, minus 3 and so this is called the folding. Let's say it has been given that x of t is equal to x of u of t plus 3. Plot x of minus. Mathematically how you are going to write? So simply x of minus t, wherever you have t, make it minus. Okay. So how will you plot? First of all, plot the x of t. First of all, the x of t, ut plus 3, that means advanced by 3 unit. Advanced by 3 unit, that means it looks like if it is a 0, 1, 2, 3. Because ut starts at t equal to 0, but ut plus 3, that means ut advanced by 3 unit. So like this. Now you fold about the origin. When you put a mirror here and you look, double-sided mirror, obviously signal is existing both the side, so you have to use a double-sided mirror. When I put a mirror here and look at this will be reflected here, and if I put a mirror here, look at this mirror here and look from this side, I will see only this line. So obviously this function looks like this. Like this is your x of minus t. Another way, whether you have drawn it correctly or not, just put this value x of 3. When I put this value x of 3, so minus 3 plus 3, 0, okay, it is existing. Some other value, like I have shown this value is existing. So let's say I put the 1 or minus 1, let's say minus 1. So u of minus 1 plus 3, that is u of 4 existing. but whether you have correctly drawn. So let's see that u of 4, u of t equal to 4, minus 4 plus 3, that is u of minus 1, yes, 0, right? U of minus 1 is 0, yes, u of 4 is 0, 0 as it is shown in the figure. So these are the ways you can easily verify whether your operation is correct or not. Let us move to the scaling operation. Let x of t is your signal, right? Scaling operation defined as x of alpha t. For alpha can be positive or negative. X of alpha, magnitude of alpha less than 1, it is called the linearly stretched. Linearly stretched. For alpha, magnitude alpha greater than 1, it is linearly compressed. Linearly compressed. I will show by the example. Let x of t is shown like this. That is your 1, let's say 1, your 1, and this is your 3. Okay. Now what I do, I need to find x of, first one is the magnitude of alpha less than a linearly stretched. Less than 1 means, let's say I do like this, x of t by 2. Alpha is equal to half, which is less than 1. So the signal will be linearly stretched. Stretch means it will be wider. Wider means what will happen? You will multiply to both the values, both the time point, or you can say coordinate point of the time. It will be, let's say, the value remains same, but it is linearly stretched by 2 factor 2. So 1 into 2, 2, 3 into 2, that is 6. That is from 2 to 6 now. Earlier it was 1 to 3, duration of the 2. Now you see the duration will be the 6 minus 2, that is 4. That is, linearly stretched by the 2 unit, linearly stretched. When you divide it by 3, it will be linearly stretched by 3 unit. You can check. That is the linearity, how we call the linearly stretched or linearly compressed. Now x of 3t, alpha is greater than 1. So what do we expect? It will be compressed, signal will be compressed. So for that we will be dividing by all this. This is 1 upon 3, this is 1. This is 1 upon 3 and this is. So you can easily say that the duration becomes 1 minus 1 upon 3, that is 2 by 3. You can see that linearly compressed by factor 3, that is we divided the duration by 3. Now 1/3 of the original duration, yes or no? This is now 1/3 of the original width. Original width is 2. Now it is 2 by 3. Hope it is clear. So we have previously discussed the Laplace transform pair. We have left one Laplace transform. Few Laplace transform has been left there. So once again I will write the full table which will be looked into. As you know that a constant, a step function ut or a voltage u and ut, that is a voltage source is there v, or a step function or a voltage source is existing, okay, and you are switching it, okay, at t equal to 0, it is equivalent to this. Originally there is no voltage source connected, now at t equal to 0 the voltage is v. So I write v u of t, as you know, v upon s, because ut is 1 upon s, del t as usual 1, then ramp rt is the t ut, okay, which is 1 upon s square. Similarly, suppose only t ut, but let's say t to the power n ut. So this is n factorial upon s to the power n plus. This is the one property, differentiation property. You can easily we'll discuss that property. Like from the definition itself, you can get it. The definition was Laplace transform was like this: x of s was the 0 minus to infinity x of t e raised to the power minus st dt. Now we differentiate with respect to s. dxs upon ds is equal to, because it is integration about the time, so you can easily differentiate. When I differentiate, what I get with respect to s, so I get the minus t e to the power minus st dt. So I take out the minus here, so minus 1 dxs ds is equal to 0 minus to infinity txt txt e to the power minus st dt. Now you can see that here, so tx of t, okay, so your tx of t has the Laplace transform of minus 1 dxs ds, okay. Now use these relations, okay, again and again. For example, t square xs as the minus 1 to the power square t square xs upon xs, okay. Just take the xs as ut, so you will get the answer t ut. So you see here minus 1 and d upon ds of 1 upon s, that is minus 1 into minus 1 upon ss, that is 1 upon s. And again do for this, and you will ultimately you will get the this is the general relations, okay. For example, suppose you multiply t and this xt is the e to the power minus at, okay, ut. So it is simply, when you differentiate it, you will have here 1 upon s plus a square, here a greater than b, okay. So I am so these are the transform, okay. Then another transform is the, suppose it is t to the power n e to the power minus at ut. So you will have then n factorial upon s plus a n plus. So this is the this is the transform pair. And we also before that we have also considered sin at, cos at, e to the power b sin at, a to the power minus b at. Okay, this is over. Then properties, okay, important. First property, let x of t has the Laplace transform of x of s. So e to the power a t xt has the Laplace transform of x of s plus a. This property we have used here. You see, this one, e to the power a t xt. See, this is the xt. For example, xt is a t to the power n. Wherever you have a s, you need to replace with the x plus a. So if you are still confusing, let us say x of t is equal to rt, right? So its Laplace transform is 1 upon s square. Now e to the power a t rt or t ut as the Laplace transform of using this property. Wherever s you should put the s plus a, that is plus a. Similarly, for example, e to the power minus at, t to the power n ut, t to the power n ut. What is the Laplace transform of xt? That was your t to the power n ut, n factorial upon s to the power n plus 1. So n factorial, wherever s you should put the s plus a, s plus a to the power. Very simple. Okay, and this property t to the power n x t square. Okay, general property here up to we found out the t square xs minus 1 to the power square d square. So suppose you have been given this property also important. This is the property number 1. Property 2, t to the power n x of t has the Laplace transform of, because we before we seen that t to the power t xn t to the power t into xt has the minus 1 dxs upon ds. So here t to the power n will be the minus 1 to the power n nth derivative of Laplace transform also Laplace transform of x of s, nth derivative of t. Okay, then folding normally does not come in picture in the network theory question, but it is a very much part of the signal and system. Is 1 upon a magnitude x of s plus a. You can easily all these things you can easily prove from the definitions. So fourth one is the convolutions. Convolution will be much more way discussed in the signal and system. Just remember it. Convolution of two signal. We are assuming that both the signals are causal. That is x of t, h of t both are 0 for t less than 0. Right? Then we call the causal. That means convolution in time domain is the multiplication in the Laplace domain or frequency domain. Convolution integral is defined as x of t, h of t, the here because both the signals are causal, so limit will be 0 to t x of tau, h of t minus tau d tau, or you can put the h of tau x of t minus tau. Okay. So now another important property I'll discuss, as network is considered LTI. Inherently we are considering the network is the LTI. Okay, network LTI, NP is LTI. So it's a very important property. Suppose you have a network and you have an input. You are getting the input can be voltage current, output can be voltage current. For network perspective, system perspective is it can be abstract, but network perspectives it is input can be voltage current or output can be voltage. This is your white, right? Then I have also demonstrated before also. If we shift the for same network, if we shift the input, okay, if I shift the input by T0, my output will be also shifted by. It's very important you should remember. That means whenever you have a smooth functions, you can easily use the Laplace transform. Okay, how you be using this? But what about this poles? How to find out? Then for that we should know the first waveform synthesis. Then this property combined with this property, we can use the. You can easily arrive at the answer. We'll discuss in the next class, because it is already we have discussed a lot of things we should go through. Then another thing is periodic functions starting from t equal to 0. Suppose you have a periodic function like this. How to find this Laplace transform? It's, let's say, x of t is equal to x of t plus n is integer. This is the definition of periodic functions, and we are assuming that for t greater than 0. So x of s, because unilateral Laplace transform, which is simply 1 minus e to the power minus ts, is the time period of the periodic functions, into x of t s. What is this x of t s? That is Laplace transform of one period. What is this period of this periodic signal? The period. This is the period. Let's say this t, and this is the, let's say, t by 3. Okay. So one period of, for one period you need to find the Laplace transform and multiply, you can get the Laplace transform of periodic signal. So what is this x of ts? X of ts is the Laplace transform of one period of signal. Because here we are discussing the Laplace transform of periodic signal for t greater or equal to. Okay, we have learned many things. Please go through all these topics and transform. You do the do your notes while having doing your notes, and if you have any doubts, you can easily discuss in the group, right? And okay, some other parts is also there, like Laplace transform of derivatives, Laplace transform integration, initial and final value theorem, then waveform synthesis, and we'll discuss in the next class, right? Because this is very important topics as far as GATE and the engineering service, all the competitive exam, they actually people neglect this transient analysis part. So I don't want to run through these materials. Instead, I want to go slow so that you can observe all the nitty-gritty of these topics. and you must be able to apply all the theory learned, not only in the exam but also in the doing the um, calculation in the other topics like VLSI design, and where else transient, digital circuit design. Whenever mixed, actually normally transient you will be found in the mixed signal processing, right? Like you have a operational amplifier, you have a capacitors, and you have a switch. So that will be when you close the switch, capacitor will start charging at certain point of the time. The operational amplifier output will goes some set value, and that will trigger a digital circuit, and that will trigger the other component in cascade. So normally these are the uh, transients are largely used, or you can say the always substantially used in the mixed signal design and digital circuit also. Anyway, please keep learning. As you know that your each day passed, you must add some extra knowledge to your knowledge bank, and always you should practice. So that, I mean to say, I always say that people should practice each and every day. Let it be 10 questions, whatever the topics may be, be it a signal, be it a control, be it a digital, wherever you find the question, try to solve it. And as you are learning these days the network theory, that's why I am saying that you can solve the question from network theory. Till now we have covered many topics of network theory. You can solve whatever the topic. No, there is no worry, but you should practice. That will make you to be in inertia of solving the question till your GATE exam. With this, we end the class for the day. See you in the next class. Take care. Bye bye. Have a good day.